we take a number of samples from this normal distribution, and we can calculate the average of that sampling distribution. That is the same as of the original distribution, but the standard deviation is different, is namely equal to the standard deviation of the original distribution divided by the square root of n. Okay? You see this difference? Do you? Well, some people seem to be very convinced. Other people may have fallen asleep by now. If you have a problem with this, let me know. Is there a problem with this? It's clear that we go from we have two distributions. So one which we take the samples, and then we make a sampling distribution. So if we would take different samples from the original distribution, we can calculate the sampling distribution. That sampling distribution will have the same average, but the same mean, but a different standard deviation. Okay, so then the central limit theorem says that if we have x1, x2 to xn random sample of size n from a population with mean mu and variance sigma squared, this x big X bar, the sample mean, the limiting form of the distribution, which is given here, is the standard normal distribution if we have n going to infinity. Okay, so this is an important theorem. Why? Because it says that independent of what our starting distribution is, if we take a sample which is large enough, going to infinity, in practice this is 20 to 40 should be sufficient for the sample size, we can then assume that if we make this transformation, that we have a standard normal distribution. So basically, it allows us to use the standard normal distribution, probabilities, the tables for that, on the sampling distribution. Okay? So that makes our lives much easier. And so to show how that works, so if you have this as the original distribution, this is a die, and so the probability of having 1, 2, 3, 4, 5, or 6 is equal. Yeah. So if you then throw the dice a number of times, you see that you start approaching something that looks like a normal distribution. Okay? So this is the central limit theorem, which we'll use quite often as we go along. All right, so an example of that, and I will pass on to you.
Distribution of x is approximately normal with a mean of 100 and a standard deviation of 2. Therefore, the desired probability corresponds to the shaded area in figure 3.24. Standardizing the points x is 95. We find that set value is minus 2.5. From the points, and therefore the probability of x being less than 95 is the same as that's smaller than minus 2.5, which
okay. So what have we said here? What have you said? That we can use the standard normal distribution because n is 25 is close enough to infinity. So that's the approximation that we make. And then for this normal distribution, this is now the standard deviation. So we divide through with square root of n. We're going from something which had a standard deviation of 10. Okay, and so this is the transformation we make. The value minus the average divided by the standard deviation gives us the z value. And then we see what the probability is of having the average smaller than this 95 means z smaller than minus 2.5. Okay, so that's so here we make use of this central limit theorem to go from something where we don't know necessarily what the distribution is to something which is a sampling distribution which is normally distributed. All right. So let's go back to, or let's go forward rather to the next chapter, which is on decision making.
Yeah.
So it starts with decision making on a single sample, and then next lecture we'll talk about 2 or more samples. But it's the same type of reasoning, so that's why we'll probably spend a lot of time, or a fair amount of time, talking about one sample, although in practice, of course, typically you're looking at 2 samples and trying to make a comparison, or multiple samples trying to compare and trying to make a decision based on the comparison. So statistical inference is what it's called, or decision making, is based on the experiments we've done, the measurements we've made. We then make some type of estimation of what we think the population is, and then based on that we then make some type of statement which could be interpreted as a decision, okay, or could lead to a decision. So we'll make some statements on probabilities of having a particular situation, and for that we need to understand about errors, type 1 and type 2 errors that we can make, so that when we make a decision, we also understand what the risk is of having made the wrong decision. Because this is the sad thing about statistics, that it points us to the risks we're taking when we make decisions. Okay, so we cannot, based on this methodology, make a decision which is 100% safe. So we talked about taking risks earlier. So we'll have to see what type of risk, depending on the situation, we can afford. And then based on that, either decide to do more experiments so that we have more information, or to go forward and take the risk. As an aside, academic engineers have sometimes been accused of not wanting to take risks because we want to calculate everything to 7 digits before we think we know it well enough to be able to go forward. So yes, we need to be aware of the fact that we at a certain moment we'll have to take a risk, and of course we do the best to make the risk small, but at a certain moment you have to go forward. Sometimes the biggest risk is to stay put. Okay, that's also a risk. To freeze, so to speak. So don't go into the freezing mode and start calculating until the end of your career, and then you go retire and say, I forgot to do something. So that's not where you want to be. So you want to have the right balance between having the information and moving forward, taking a risk. Okay, so the entrepreneurial aspect of our lives. It's you have to keep that balance. All right. I don't know if this rings any resonates with you. Of course, you in the university we tell you to keep calculating. So you also have to decide you want to do something. All right. So all right, let's see how we can deal with this. Okay, so we have populations, distributions, from which we then take a sample, and based on that sample, we're now going to try to make statements about the population, and based on that make decisions. So we have point estimations. A point estimate is a single numerical value of a statistic. So we talked about statistics just now. So a typical statistic is the average or the variance, which we can calculate. And if we make a specific calculation because we've taken a sample, that is then a point estimate of the statistic. Okay, so a particular value of the statistic is a point estimate. Okay, so if we run through this, we once again have a normal distribution with mean and variance given. Then we know that the distribution of the mean is normal with mean mu and variance sigma squared divided by n. So we know that the standard error is given by this. This is what we've just seen with the central limit theorem, but this is not even the central limit theorem. This is just applying the rules for linear functions, because we started with a normal distribution. Okay. If we do not know sigma, but use now the sample standard deviation, then we get an estimated standard error of the mean. Okay. So typically, even if our distribution is, we check using the methods we discussed last week. We checked if our distribution is normal, and that turns out to be okay. We don't typically know what the sigma is, so based on the sample we can make an estimate, as we've also indicated last time how to do that. Okay, so we sum the differences squared, the difference between the random variable and the mean, squared divided by n minus 1. And take the square root of that, that is s, right? And then we divide through square root of n. That is an estimate then of the standard error of x bar, the mean, the distribution of the mean. All right, so let's see how this is applied. This is coming from a paper some time back, 1974. A new method is described to measure thermal conductivity of a certain type of iron. And this is at a temperature of 100 degrees Fahrenheit, a power input of 550 watts. 10 measurements were made of thermal conductivity given there. The values, the point estimates is just the average of these, right? So that's the calculation here. The standard error is then sigma divided by square root of n. Sigma we don't know. We don't know what this sigma is for this Armco iron. So we replace this by the standard deviation S, which if you calculate from this series of numbers would be 0.284, and then the standard error on the sampling distribution, the mean distribution, is equal to S divided by the square root of n. I think you know this, but still sometimes people get confused by this. Right? So obviously by increasing the sample size, we get a lower standard deviation on the sampling mean and on our estimate of the mean of the original distribution. Okay? All right? So even if we start off with a very wide distribution, we can still have a fairly accurate determination of the average of the distribution, or estimate of the mean of the distribution, by taking a large sample size. Right? So that's how it goes. Okay, so let's look at hypotheses. A statistical hypothesis is some type of statement that we make about one of the parameters of a population. All right, so an example is we have a solid propellant, some type of fuel with a burning rate, and this fuel is used to propel some type of aircraft. So the burning rate is the random variable. It has a certain probability distribution. And we want to see if this mean burning rate is equal to a certain value or higher than a certain value. Okay? So the hypothesis could be that it is higher than 50 centimeters per second. All right? We make some type of statement on this that the mean is higher than 50 centimeters per second. So we make some type of statement on a parameter of the population. All right, so typically when we do make these hypotheses, we either work with a two-sided hypothesis, basically saying that, and you see here H0 and H1. H0 is what we call the null hypothesis. So we state that the burning rate is equal to a certain value. The H1 is what we call the alternative hypothesis. In this case, it's a two-sided alternative hypothesis. Why? Because we just state that the mean is different from the value. We can also have one-sided alternative hypotheses, for instance, stating that it's smaller or higher than this value of the null hypothesis. Okay? So we basically have two opposing statements for a particular situation. Okay? A null hypothesis and an alternative hypothesis. Null hypothesis we indicate with H0, alternative with H1. All right? So then we can start to test the hypothesis that we make. And for that we use a particular procedure to do that. And so we use information based on what we know on the population. So that what we know of the population is based on a sample of the population. And then we see on the properties that we can derive from the sample how this information is consistent or inconsistent with the hypothesis. So if it's consistent, we say the hypothesis is true. If it's inconsistent, the hypothesis is false. Okay? So for instance, for our situation of the burning rate, so the null hypothesis is 50 centimeters per second for the burning rate. And we have a two-sided alternative hypothesis stating that it's different from 50 centimeters per second. So the way we then do this is we define a region around the value of the null hypothesis, where we say that if our measurements, the average of the sample would be in this region here, then we say it's close enough to 50 centimeters per second so that we cannot say our null hypothesis is false, so we fail to reject it. Okay? We're not actually saying it's true, but we cannot say that based on our data we have enough information to say that this is not going to be. Okay, so we say it's close enough, so we fail to reject the null hypothesis. If we get far away from the null hypothesis value, then we have information which says that, hey, this seems to be not okay, and then we say, okay, our null hypothesis is not okay, and we reject it. All right? So this is kind of the general mode of thinking. And when we do this, we make errors. And this is always a little bit tricky. There's two types of errors, type 1 and type 2. So rejecting H0 when it is true is a type 1 error. Failing to reject the null hypothesis when it is false is a type 2 error. So to clearly show how it works, so we make a decision. Our decision is of two types. We cannot reject, we fail to reject H0. When H0 is true, that's fine. When H0 is false, then we make a type 2 error. If we reject H0, but it is true, then we have a type 1 error. If it's H0 is not true, the null hypothesis is not true, is false, then we have no error. Okay? This type 1 error is also called significance level or alpha error, or sometimes also size of the test. All right? So, and now we get back to the central limit theorem. And so if we have our sampling, we have our sample, and from our sample we calculate the mean, if our sample is large enough, or if the underlying distribution is normal, then we can assume that the distribution of the mean of our sample is normal. Okay, so that's why we draw this normal shaped distribution. All right, so and if we once go back to our situation of the burning rate, we see that we have once again indicated our critical values for which we change our decision. So our type 1 error, meaning the error is, type 1 error is where we decide to consider our null hypothesis false when it's still true, and say true meaning the distribution is centered around the value of 50. Because of the fact that we have this distribution, there is still a probability of having values outside of the range. And so that's our type 1 error, right? And because if we would come up with a mean here, it's possible, according to the distribution of our means. It's possible, it's not likely, but it's possible. And so if we integrate the areas outside of the critical values, that is the probability that we would still measure a mean falling outside of that region. So it's going to lead to a decision stating that we have to reject H0, but H0 is still true. So this is our type 1 error. Okay? Are you following that? Yeah? Some people are nodding, some people are quiet. So maybe it becomes more clear if we run through this this here, especially what I've said. But let's run through it systematically. We make our decision based on random variables, so we don't know what the true distribution is. So based on the random variables on our measurements, we have to make a decision. Okay, so the type 1 error we said is the probability of rejecting H0 when H0 is true. All right. As we said, it's also sometimes significance level or size. And so in the case that we're studying here, the burning rate, we have a type 1 error when the average, so the point estimate that we make, is larger than the upper value that we've indicated for the region, which we still consider to be close enough to 50, or smaller than the lower boundary of that region, 48.5. When the true mean burning rate is 50 centimeters per second. So we assume that the true mean burning rate is the value which we've chosen for our null hypothesis. Okay? And because that's our assumption, that's the hypothesis. All right, so the burning rate has a distribution for the conditions of the central limit theorem. So the null hypothesis is true. The distribution of the sample mean is approximately normal with that mean and a standard deviation which is equal to the standard deviation of the population divided by the square root of n. That's 0.79. Okay? So the probability of making a type 1 error is then equal to the sum of the areas in the shaded areas in the tails of the normal distribution. So these two shaded areas, that is our type 1 error. And so we can just then go through and calculate this if we know what the sample size is and what the standard deviation is of the underlying population, or by using the estimates that we have, or that we can make by calculating it from the sample. All right, so we can just go through the calculation. It's always the same, so you calculate the z values and find the probabilities for the z values to be smaller or larger than the boundary values. Okay, and so in this case it would be something just above 5%. Okay, so that's our type 1 error. Okay, so this brings us to our type 2 error, which is failing to reject H0, the null hypothesis, when the null hypothesis is false. That's a type 2 error. And so, how do we calculate the type 2 error? When we do that, we have to formulate an alternative. So the null hypothesis is, we said is mu is 50. Now our alternative hypothesis is that it's different from 50 or smaller or bigger than 50, depending on one or two-sided alternative hypothesis. But here in this case, we fix, to be able to calculate the type 2 error, we fix the value and say, actually, the mean is 52. Okay, so we basically say, no, the mean is not 50. And so the null hypothesis is false. It's not 50, and we give it a certain value. And we say, in this case, 52. All right, so this type 2 error is dependent on the value that we pick for the alternative hypothesis. And so then if this would be true, so if this alternative hypothesis would be true, we would once again have a distribution of the mean based on our sample. Okay? And now we can then once again see which the probability is that we would still accept H0. We would fail to reject H0. This is the shaded area which you see here, right? Because we've indicated the boundary, and so if we're left of that boundary, we would still not be able to reject H0, we would fail to reject H0. So that would then be our type 2 error, right? This is the probability of finding a mean which is in the region where we fail to reject H0 under the condition that the mean is 52. Okay? And this is for a sample size of 10, and this is for a sample size of 16. So do you see the difference? Is there any difference between these two curves? Between sample size 10 and sample size 16? Yeah, what? Yeah, so this, if you look at 50, you can see it here. 50, you still see something which is clearly different from 0. Here it's not that clear. So yes, you squeeze down this distribution. Does that make sense? That it's narrower? Yes, because it's sigma divided by square root of n. Okay, and now n is 16 as opposed to 10. So this will squeeze down the distribution on both sides, right? Also this one, if you look at 52, also this one is now narrower because we're looking at something which is our sampling mean distribution, which is sigma divided by square root of n. Right? Of course, if you take H1 to be 50.5, then the probability of failing to reject H0 when H0 is false increases dramatically, right? Because now, as the differences become very small, we see that there is a large overlap between these two. Okay? So to run through this again, so to calculate type 2 error beta, we need a specific value for the alternative hypothesis. So as we said, we take in this case mu is 52, or we could also take mu is 48, and work based on these values. Of course, you can ask yourself the question, why 52? Why not 55? Why not 51? 52, you take 52 because 52 makes sense to you, okay? Because that's 52 to you is different enough from 50 for you to be sensible. If you say 51 or 50 doesn't matter, but if it becomes 52, it does matter for me, then you take 52. If it's only 55 that's meaningful to you, you take 55. Okay? So it depends on the person who's doing the experiments, of course, what that value is, or the situation, rather than the person. Hopefully the person is sensible enough to understand the situation and picks a value which is sensible. Alright, so now we can calculate this type 2 error by looking at what we have. Okay? So this beta type 2 error is the probability of having our average between 48.5 and 51.5. The boundaries which we have indicated as the boundaries for which we fail to reject H0. These are the boundaries. For mu now equal to 52. So we then need to do the calculation of the z values for this. So we take the boundary value minus 52 divided by the standard deviation. We do the same thing here. And this gives us two values for z. And so beta is then p z smaller than the probability of z being smaller than this value, minus the probability of z being smaller than that value. Okay, so if you go back to our drawing, maybe this one is easier. We need to take the area under the distribution going from minus infinity to this value, minus the area which is going from this value, this boundary, to minus infinity. So that area. Okay, you see that? Because if we would have a value here, we would also reject the null hypothesis. Okay? So, of course, that value, this p of z smaller than minus 4.43 is, of course, extremely small. So we can just focus on this p value. And so that gives us 0.2643. Okay, so this type 2 error gives us an indication also on a risk, namely the risk of not recognizing the fact that our null hypothesis is false. Okay? So we still we fail to reject the null hypothesis when it is false. And that's, of course, also an error which we need to be aware of. And so, depending on how we set up the experiment, we can limit type 1 and type 2 errors. And we'll talk about that next week. All right? So, have a nice